Hi students, in today's session we are going to discuss how to determine the image position due to reflection by a single spherical surface using paraxial approximation technique. In the last class we had used paraxial approximation technique to determine the image position due to refraction by a single spherical surface. Now let us just discuss once again what is paraxial approximation technique. Paraxial rays are those which make very small angles with the principal axis, so that in the paraxial approximation technique the incident rays are nearly equal to 0, or the angle of incidence is nearly equal to 0, or all the subtended angles are nearly equal to 0, or very small angles. Okay, so that the sine of the angle, tan of the angle, etc. can be approximated to that angle itself, to the value of the angle itself. So let us come to the image formation due to reflection by a single spherical surface. Let us determine the image position using paraxial approximation technique. So the figure here is as shown below. Okay, so this is the, what you see here is the spherical reflecting surface, and this is our object, point object O, and this line here represents the incident ray, and the angle here is the phi 1, represents the angle of incidence, and this ray coming back after hitting the mirror surface is the reflected ray, this one, and the angle here, that is phi 2, represents the angle of reflection. So as you all know, by the laws of reflection, angle of incidence must be equal to the angle of reflection. So the angle of incidence here is phi 1 and angle of reflection is phi 2. I express both these angles in terms of alpha 1, beta, alpha 2, etc. So phi 1, from this figure, you consider this triangle, that is the triangle having one side as this, the second side as this small length here, and the third side as this normal. This is the normal to the surface. So this small triangle, so this angle is phi 1, this angle here is alpha 1, and this exterior angle is beta. We know that exterior angle is equal to the sum of the interior opposite angles, or beta is equal to alpha 1 plus phi 1. So what is phi 1? Beta minus alpha 1. So phi 1 is equal to beta minus alpha 1. Similarly, we write down what is phi 2. What is phi 2 here? For that we consider the next, this triangle here, this one, the dotted line as, that is our normal as one side, the small side here as the base, and this one as the third side. So that this angle is phi 2. So alpha 2, that is the exterior angle, is equal to beta plus phi 2, or phi 2 is equal to alpha 2 minus beta. Okay, so I'll show you the angles as rewritten here. So phi 2 is equal to beta minus alpha 1, as we saw from the figure, and phi 2 is equal to alpha 2 minus beta. Now what is beta, alpha 1, alpha 2, etc.? So once again we come back to the figure. Now h is the perpendicular distance between the principal axis and the point where the incident ray hits the mirror surface. Then the distance between this image and the mirror surface is given as y. the distance between the center of curvature and the mirror is represented as r, small r here, and the distance between the object and the mirror surface is represented as x. Now using these informations, we represent alpha 1, beta and alpha 2. Now what is alpha 1? We know tan alpha 1 is equal to opposite side by adjacent side, that is h by x. Since we are using paraaxial approximation technique, these alpha 1, beta, alpha 2 are all very small angles. So tan alpha 1 is nearly equal to simply alpha 1. So alpha 1 is equal to h by, you can write alpha 1 as equal to h by x. Okay. So what is the next angle now? Beta. Beta is equal to h by r. Alpha 2 is equal to h by y. We make these substitutions here in the equations for phi 1 and phi 2. So phi 1 is equal to beta minus alpha 1 is equal to h by r minus h by x. Phi 2 is equal to alpha 2 minus beta is h by y minus h by r. By laws of reflection, phi 1 must be equal to phi 2. So I equate these two, h by r minus h by x equal to h by y minus h by r, so that I get h by y plus h by x is equal to 2h by r. H can be taken common factor, it can be cancelled off from both the sides, so that you get 1 by y plus 1 by x is equal to 2 by r. Now we can replace y, x and small r by small u, small v, that is small u is our object distance, small v is our image distance, and capital R the radius of curvature, and apply sign conventions. Last class we had discussed the sign convention. We had told that if the object is kept at the left side of your spherical surface, if it is kept on the left, then the distances on the left side is considered as negative, and that to the right are considered as positive. That is, if the object is kept on the left, then left of the spherical surface, then all the distances on the left are considered to be negative. So here y is negative, r is negative, x is negative, or y, which is small v, is minus v, capital R is minus r, x, which is u, is also minus u, because all the distances are towards the left of the mirror, left of the spherical surface. Okay, so you can apply it here. So you can see what we have written here. X is equal to minus u, y equal to minus v. So 1 by u plus 1 by v is equal to 2 by r. So 1 by u plus 1 by v is equal to, what is 2 by r? R by 2 is f. So this is equal to 1 by f. Okay. So thus we can determine the image position of due to reflection from a spherical surface. Image position means you can determine v from this equation, and the point object can be imaged. Okay. So I think the image formation in a spherical reflecting surface is clear to all of you. Next we discuss thin lens. So a medium bounded by two spherical refracting surface is referred to as a spherical lens. A medium which is bounded by two spherical refracting surfaces, like this, one like this and one like this, or one like this and the other one like this. So all these are spherical lenses. If the thickness of this lens is very small compared to u, the object distance, compared to v, the image distance, or compared to r, the radius of curvature, if this thickness of the lens here, in both these cases, if t is very small compared to u, v and r, that means such a lens is called a thin lens. So I hope it's clear to you. Any medium bounded by two spherical refracting surface, either like this convex or concave, forms a spherical lens. And if the thickness of the lens is so small when compared to U, V and R, then such a lens is called a thin lens. Okay. So by defining the thin lens, we come to the paraxial image formation by thin lens. Paraxial image formation by thin lens. So for that, we first consider a thin lens. The refractive index here outside the lens is N1. The refractive index inside the lens is N2, or the refractive index of the lens material is N2. Now we consider a point object O, and C1 and C2 are the centers of curvature of the either spherical surfaces, faces. Let R1 and R2 be the radii of curvature on the right side. This one, C1 is the center of curvature here. So R1 is the radius of curvature on the right side, and C2 is the radius of curvature on the left side. If O is the object, then here this distance x is the distance from O to the lens. If I is the position of the final image, then it is the this y is equal to v, which is the distance of the final image from the lens. So we'll go to the explanation. We have considered a point object here placed on the principal axis of the thin lens. Then the lens is placed in a medium of refractive index N1, and the refractive index of the lens material is N2. Capital R1 and R2 are the radii of curvature of the right and left surfaces of the lens. So that R1 is positive and R2 is negative from sign convention. Now to determine the position of the image, we can consider the successive refractions from the two surfaces. Now here there are two refracting surfaces. One on this one, and the other one is this one. So we can first consider the refraction from one surface, the image formed due to that, and this image will act as the object for the second refractive index, second refracting surface, which will give you the final position of the final image. Now let us see how this is done. So to determine the position of the image, we consider the successive refractions at the two refracting surfaces. First, the image formed by the first refracting surface is considered, and then this image is taken as the object for the second refracting surface. നിങ്ങൾക്ക് മനസ്സിലായി കരുതണോ? അതായത് ഒരു റിഫ്രാക്റ്റിംഗ് സർഫസിനെ ആദ്യം കണക്കാക്കി അതിൻ്റെ ഒബ്ജക്റ്റ് എന്ത് ചെയ്യും? ഈ ഒരു റിഫ്രാക്റ്റിംഗ് സർഫസിൽ നിന്ന് ഒരു ഇമേജ് ഉണ്ടാക്കുന്നു. ആ ഇമേജ് രണ്ടാമത്തെ റിഫ്രാക്റ്റിംഗ് സർഫസിൻ്റെ ഒബ്ജക്റ്റായി മാറി യു ഗെറ്റ് ദി പൊസിഷൻ ഓഫ് ദി ഫൈനൽ ഇമേജ്. അതിൽ നിന്ന് കിട്ടുന്ന ഇമേജാണ് ഈ ലെൻസിൻ്റെ ഫൈനൽ ഇമേജ്. സോ വി ഫസ്റ്റ് കൺസിഡർ ദി ഫസ്റ്റ് റിഫ്രാക്റ്റിംഗ് സർഫസ്, ദിസ് വൺ. Okay, the first refracting surface is considered. So this is the object here, the point object. The incident ray goes and you get the image at Q. Okay, so this dotted line represents the normal to the surface. So O to the first refracting surface, this distance is U. Then the distance from the refracting surface to C1 gives you R1, and the distance from the refracting surface to Q gives you V dash. Now this equation, Gaussian equation, we had learnt in the last class. So the equation was N2 by V minus N1 by U equal to N2 minus N1 by R. So in this case it is N2 by V dash minus N1 by U is equal to N2 minus N1 by R1. Now this Q acts as the object for the next refracting surface, the second refracting surface. Now that I have drawn here, the second refracting surface is drawn here. So Q acts as the object. Again I have drawn the normal, and this is the position of the image that we get. Okay, so here we consider, instead of here, the second medium is N1 now. So N1 by V, which is the image position, final image position, minus N2 by V dash, which is the U here now. So N1 by V minus N2 by V dash is equal to N1 minus N2 by R2. This is our second equation, the Gaussian equation for the second refracting surface. Now what we do is we add 1 and 2. We can add them because the distances are taken from the center of the lens, and the lens is very thin. If the lens was thick, then the thickness of the lens should also have been taken into consideration. But here we need not take that, and we can directly add these two equations because our lens is very thin. So what happens is, this term N2 by V dash gets cancelled off, and what is remaining is N1 by V minus N1 by U is equal to N2 minus N1 into 1 by R1 minus 1 by R2. I take N1 common factor out from both these sides, and I bring it to the RHS. So it becomes 1 by V minus 1 by U is equal to N2 minus N1 by N1 into 1 by R1 minus 1 by R2. So the equation becomes, this is our first part, this is the second refracting surface. So our final equation is 1 by V minus 1 by U is equal to N2 minus N1 by N1 into 1 by R1 minus 1 by R2, or 1 by V minus 1 by U is equal to, I divided both these terms by N1, N2 by N1 minus 1 into 1 by R1 minus 1 by R2. N2 by N1 can be written as simply N. Okay, refractive index of the second medium by first medium can be written as simply N. So 1 by V minus 1 by U is equal to N minus 1 into 1 by R1 minus 1 by R2. This is quite familiar to you. This is the thin lens formula. This equation is usually written in the form 1 by V minus 1 by U is equal to 1 by F. That means, comparing these two equations, 1 by F is equal to N minus 1 into 1 by R1 minus 1 by R2. So I hope whatever has been discussed is clear to all of you. How we found out the image position, that is 1 by V, can be found out using paraxial approximation techniques in the case of a thin lens. In thin lens, our paraxial approximation technique gives us V as per this equation, 1 by V minus 1 by U is equal to N2 by N1 minus 1 into 1 by R1 minus 1 by R2. R1, R2, N and U is known to us, then we can calculate the image position V using the thin lens formula. So I hope this session is clear to all of you. If you have any doubts, please do contact. Thank you.